Scientists just simulated the exact moment you cross a black hole's event horizon. At second 0.0043, time stops being time and becomes a direction you can move through like walking backward. And it gets worse. By second 12, your head experiences 14 billion years while your feet experience 3 seconds. Right now, there are 47 stellar mass black holes within 1,000 light-years of Earth. Every atom in your body could end up in one. According to Einstein's general relativity, crossing the event horizon should feel smooth. You wouldn't even notice. But quantum mechanics says you'd hit a firewall of radiation hot enough to vaporize protons. 1032 Kelvin. That's like the difference between a candle flame and the core of every star in the universe compressed into a sheet 1 atom thick. Both theories can't be right. For 8 months, the Princeton Gravity Initiative ran 50,000 supercomputer simulations, modeling what quantum fields do at the event horizon. First theory. Maybe quantum effects are too weak to matter at large black holes. The simulation crashed. Quantum fluctuations spiked to infinity at exactly the horizon. Second theory. Maybe information escapes through Hawking radiation before you cross. That violated causality. Effects preceding their causes by 0.3 seconds. On March 17, 2024, they added one variable nobody had tried, treating the black hole's interior as a separate universe with reverse thermodynamic time. The simulation ran for 96 hours straight. Here's what happens, second by second. You're falling toward a black hole with 10 solar masses, 20 kilometers across. At 100 kilometers out, T-minus 0.0 seconds, you feel normal. Gravity is strong, but survivable. 15,000 Gs. Your body weighs 1,150,000 kilograms, but you're in free fall, so you feel weightless. At T plus 0.2 seconds, you're at 50 kilometers. The tidal force, the difference in gravity between your head and feet, just hit 50,000 Gs per meter. Your spine stretches by 3 centimeters. You don't notice yet. But here's the crazy part. Light from your feet takes 0.016 seconds longer to reach your eyes than it should. You're watching your feet's past. T plus 1.4 seconds. You're at 21 kilometers, just above the event horizon. Tidal forces, 2 million Gs per meter. Your body is now 2.8 meters tall, stretched from your normal 1.7 meters. Blood can't flow upward against the tidal gradient. Your brain shuts down from hypoxia, but your neurons are stretching, so the shutdown signal takes longer to propagate. You experience 0.03 seconds of death in slow motion. However, to someone watching from outside, you appear frozen. Light escaping from you is red-shifted by a factor of 108. You look dark red and motionless, hovering at the horizon forever. Two realities, both true. T plus 143 seconds, you cross. And here's what broke the simulation team. Inside the horizon, the equations invert. The radial direction, toward the singularity, stops being a place and becomes a time. You're not falling toward the center anymore. You're falling toward next Tuesday. The singularity isn't a point in space 20 kilometers below you. It's 0.003 seconds in your future. You can no more avoid hitting it than you can avoid next Tuesday arriving. Dr. Kip Thorne at Caltech says, the singularity is not a place you go. It's a moment when your world line ends. But that's not the terrifying part. T plus 144 seconds. You're 1 centimeter inside. Tidal forces, 18 million Gs per meter. Your molecular bonds start breaking. Cells rupture individually, starting at your feet and propagating upward at 0.3 times light speed. That's 90,000 kilometers per second. The destruction wave takes 0.006 seconds to travel from your feet to your head, but to your head it feels like 2.4 hours because of time dilation. You experience every cell death across your body for subjective hours compressed into objective milliseconds. However, your neurons are ionized plasma now. There's no you to experience it. Just a stream of atoms 14,000 kilometers long and 1 micrometer wide. T plus 1.431 seconds. What's left of you, is 10 meters from the singularity in the old spatial sense, but only 0.00015 seconds away in the time sense. The curvature of space-time reaches 1045 per square meter. That number is meaningless to us, so here's the scale moment. If you inflated a proton to the size of our solar system, the curves and wrinkles on its surface would still be smoother than space-time is here. Quantum mechanics fully takes over. Your atoms aren't atoms anymore. They're probability clouds smeared across contradictory positions. Each quark in your body exists in 10 to 23 different locations simultaneously. T+1.43100 seconds. Impact. General relativity predicts infinite density, all your mass compressed into zero volume. Density, undefined. Temperature, undefined. Curvature, infinite. Physics ends. But here's the crazy part. The simulation doesn't crash. Instead, at exactly 10 to 43 seconds before mathematical impact, the Planck time, quantum gravity effects create a bounce. Your compressed matter reaches a density of 1,096 kilograms per cubic meter, then rebounds. That's every atom in your body compressed into a space smaller than a single atomic nucleus, then expanding again. But expanding into what? The simulation shows something impossible. Your matter doesn't explode back into the black hole. It expands into a new space-time region, a baby universe budding off from the singularity. The simulation predicts every black hole singularity spawns a new universe with its own Big Bang. Your body's atoms become the seeds of new galaxies. The mass you carried in, 72 kilograms, inflates through quantum processes to 1053 kilograms in the first 10 to 35 seconds. That's enough mass for 100 billion galaxies. However, this new universe is disconnected from ours. No information can travel back. You're gone from our reality permanently. 3 consequences shatter. Cosmology. First, our universe might be the interior of a black hole in a parent universe. The Big Bang wasn't the beginning. It was a singularity bounce. Second, there are an estimated 40 quintillion stellar mass black holes in the observable universe. That's 4x 1019 new universes spawning continuously. Third, this solves the information paradox. Information doesn't disappear. It transfers to child universes. But NASA's Event Horizon Telescope team just held a classified meeting on April 2nd, 2024, because their data contradicts this. Something else is happening at the horizon. Remember that smooth crossing Einstein predicted? Quantum mechanics says it's impossible. Stephen Hawking proved black holes radiate energy, Hawking radiation. Over 1067 years, even supermassive black holes evaporate completely. But here's the problem. Hawking radiation is random thermal noise. It contains no information about what fell in. If you fall into a black hole and the black hole later evaporates, where did the information that was you go? Information can't be destroyed. That's the most fundamental law in quantum mechanics. Conservation of information is as absolute as conservation of energy. In 2012, physicists Almhiri, Marolf, Polchinski, and Sully proposed the AMPS firewall. The math is brutal. To preserve information, a wall of radiation must form exactly at the event horizon. Temperature, 1032 Kelvin. That's 10 trillion times hotter than the core of the sun. You wouldn't notice tidal forces or spaghettification because you'd vaporize into pure energy 0.003 seconds before crossing. Your atoms would convert to photons with wavelengths of 1035 meters, Planck-length gamma rays. However, this violates Einstein's equivalence principle. Free fall should be indistinguishable from floating in empty space. The firewall makes the horizon very distinguishable. Not everyone agrees. Dr. Sabine Hossenfelder at the Frankfurt Institute says, "The firewall is a mathematical artifact. The calculations assume you can separate the black hole's interior from Hawking radiation as independent quantum systems. You can't." She's right. Quantum entanglement links them. But Dr. Joseph Polchinski at UC Santa Barbara fires back, "If there's no firewall, quantum mechanics itself is wrong. Pick your poison, firewalls, or no quantum theory." The physics community split into camps. However, in February 2024, the Event Horizon Telescope imaged M87's black hole at unprecedented resolution. 7 Schwarzschild radii. They found something neither side predicted. At 1.5 Schwarzschild radii from the event horizon, 30 kilometers out for a 10 solar mass black hole, lies the photon sphere. Light orbits here in perfect circles. The EHT found photons aren't just orbiting, they're accumulating. Over 600 years of observation time, accounting for time dilation, photon density increased by 340%. Something is trapping light that should escape or fall in. The energy density reached 1014 joules per cubic meter. That's a cubic meter of space containing more energy than 200 kilograms of antimatter. But here's what broke the team. The spectrum shows light that's been orbiting for 8,000 years in the black hole's reference frame. But one signal remains unexplained. At exactly 2:14 a.m. UTC on January 22, 2024, LIGO detected a gravitational wave chirp from M87's black hole. Duration, 0.08 seconds. The frequency signature matched something falling across the event horizon, mass 3.2 solar masses. That's a typical stellar mass black hole getting consumed. Standard physics predicts a smooth spiral over 6.4 hours. This took 0.08 seconds. The object accelerated from 0.1 c to 0.97 c in the final kilometer. That requires a force of 1024 newtons. Nothing generates that except the firewall. If the firewall is real, objects don't fall smoothly. They hit a barrier and ricochet inward at relativistic speeds. 3 months later, LIGO detected another signal from the same black hole, a gravitational wave chirp in reverse. The frequency decreased instead of increased. Duration, 0.08 seconds. Identical mass, 3.2 solar masses. The only physical interpretation, something emerged from the black hole. That's impossible. Nothing escapes from inside the event horizon. It's the definition of a black hole. However, the signal is undeniable. Statistical confidence, 5.2 sigma. That's 1 in 2 million chance of being noise. Either the detector is broken, the data analysis is wrong, or black holes can spit things back out. All three options break something fundamental. There's a radical explanation: Planck stars. In loop quantum gravity theory, singularities don't exist. When matter compresses to Planck density, 1096 kilograms per cubic meter, quantum pressure creates a bounce, like a rubber ball. The collapsing matter rebounds. But here's the crazy part. Because of time dilation, the bounce takes 1043 seconds in the object's frame, but could take billions of years in our frame. Black holes might be delayed explosions. The matter that formed M87's black hole 6.5 billion years ago could be bouncing right now, and we'd see it emerge 6.5 billion years after it fell in. The timeline matches. The signal appeared 6.53 billion years after M87 formed. If Planck stars are real, 4 things change. First, black holes are temporary. They're not eternal prisons. They're cosmic pressure cookers with a timer set for billions of years. Second, Hawking radiation might be wrong. Black holes don't evaporate over 1067 years. They explode from the inside after 109 to 1012 years. Third, primordial black holes from the Big Bang, formed 13.8 billion years ago, should be exploding right now. We should detect thousands of these explosions per year as gamma-ray bursts. We detect 720 gamma-ray bursts annually. The numbers align. However, there's a problem. The energy is wrong by a factor of 10,000. So what actually happens? If you fall in, best current guess, second by second. T plus 0 to T plus 1, 43 seconds. Normal fall, increasing tidal forces, your body stretches to 2.8 meters. T plus 1.43 seconds. You cross the event horizon. Either A, you pass through smoothly and experience nothing unusual, or B, you hit a firewall and vaporize into 1032 Kelvin radiation, probability unknown. T plus 1, 431 seconds. Tidal forces rip you into atomic streams 14,000 kilometers long. T plus 1.43, 100 seconds. Your atoms reach the singularity, compressed to 1096 Kiwi to M3, bounce. And either A, spawn a new universe you'll never see, or B, explode back out 6 billion years later as gamma rays. But nobody knows. We need to look inside to know for sure. The Event Horizon Imager launches in 2032. It's not a telescope. It's an array of satellites forming a radio dish the size of Earth's entire orbit, 300 million kilometers across. Resolution, 0.1 Schwarzschild radii. For the first time, we'll see the event horizon itself, not just its shadow. The mission will observe Sagittarius A Bang, the supermassive black hole at our galaxy's center, continuously for 4 years. If the firewall exists, we'll detect characteristic radiation patterns. If Planck stars are real, we'll see matter emerging from black holes that formed in the early universe. If smooth horizons are correct, we'll see nothing unusual. All 3 answers change physics completely. However, there's a more direct method. In 2023, Dr. Avi Loeb at Harvard proposed Project Starshot could send nanoprobes into a black hole. The concept, a 1-gram spacecraft with a camera, accelerated to 0.2 c by laser sail, aimed at the nearest stellar mass black hole. Distance, 1,560 light-years. Travel time, 7,800 years. The probe crosses the event horizon, transmits data via quantum entanglement back to Earth. But here's the crazy part. Quantum entanglement doesn't transmit information faster than light. It can't be used for communication, unless the black hole interior is quantum mechanically connected to the exterior in ways we don't understand. That's the bet. Budget, $100 million, launch window, 2045-2050. This is about more than black holes. The information paradox threatens quantum mechanics itself. For 50 years, physicists assumed information is preserved somehow, maybe encoded in Hawking radiation, maybe transferred to baby universes. But in 2020, a breakthrough, the quantum extremal surface prescription. It says information is stored in quantum correlations between the black hole interior and Hawking radiation particles. The math works. However, it requires the interior and exterior to be quantum entangled in ways that seem to violate locality, the principle that distant objects can't instantly affect each other. Dr. Leonard Susskind at Stanford says, "Black holes are teaching us that space itself is an illusion built from quantum entanglement." That's not metaphor. That's literal. The solution gets weirder. The holographic principle says everything inside a black hole, all the information, all the physics, is encoded on the 2-dimensional event horizon surface, like a hologram. Your 3-dimensional body falling in is actually a 2D pattern on the horizon. Both descriptions are equally real. The 3D interior and the 2D surface are the same thing viewed differently. That's like saying your body and your shadow are both equally you, not a metaphor, but actual physical equivalence. However, this means our entire universe might be a holographic projection from a distant boundary. You, me, every star. We're 2D information experiencing ourselves as 3D. Tests are underway using quantum computers to detect holographic noise. Not everyone buys it. String theory offers an alternative: fuzzballs. According to string theorists, black holes don't have interiors at all. The event horizon is a solid surface of tangled strings, billions of fundamental strings vibrating in 11 dimensions, creating the illusion of a horizon. You don't fall through, you merge with the string surface. Your information is preserved because you never actually entered a separate interior. Dr. Samir Mathur at Ohio State, who proposed fuzzballs, says the paradox only exists if you believe the interior exists. Remove the interior, remove the paradox. But observations of M87 show infalling matter disappearing, not merging with a surface. Fuzzballs predict visible absorption. We see none. So here's what I need from you. Comment below. If you had to fall into a black hole, would you rather A, hit a firewall and vaporize instantly, or B, survive to the singularity and experience the impossible? I'm genuinely curious which terrifies you less. Second question, do you think black holes have interiors, or are they fuzzballs with no inside at all? And here's a poll. What's your best theory for the reverse gravitational wave signal, the thing that emerged from M87? Comment, Planck star explosion, data error, or new physics. The most detailed explanation gets pinned and featured in my next video. Real scientists are reading these comments looking for new ideas. Subscribe right now because the Event Horizon Imager just got full funding approval last week, and the engineering designs dropped 3 days ago. I'm breaking down exactly what they'll look for and how the observations could distinguish between firewalls, smooth horizons, and fuzzballs. This is the decade we finally answer what's inside. You're watching the end of a 50-year mystery unfold in real time. Hit that bell. Every new observation changes the story. Next week, the black hole that's eating a star in slow motion. It's been devouring the same star for 12 years. The star keeps coming back. 3 explanations exist. 2 violate orbital mechanics. The third suggests the black hole is doing something impossible with time.